Hi, my name is Joshua Cook, and I'm a curriculum developer with Databricks. In this video, we're going to be doing a trivial implementation of a latent semantic analysis using Scikit-Learn. One advantage of working in Databricks is that the Databricks Runtime for ML contains many popular machine learning libraries such as Scikit-Learn, TensorFlow, and XGBoost. We will use the Databricks Runtime for ML to implement our latent semantic analysis in Scikit-Learn. There's a link to the notebook I'll be using in the video description if you would like to follow along. A latent semantic analysis consists of 4 steps. You'll note that we're using the programming language Python for this latent semantic analysis. The first step is to collect the raw text data and bring it into our environment. The second step is to convert the raw text data into a document term matrix. The third step is to perform a singular value decomposition on the document term matrix. And the final step is to look at topic-encoded data that came out of the singular value decomposition. First, let's bring in our raw text data. Here we've got the 4 documents that we've been looking at, and we've got them defined as 4 strings in a list. Using Scikit-Learn, the document term matrix can be created with the count vectorizer model. Here you can see we've imported the count vectorizer from the sklearn.featureextraction.txt module. We create a count vectorizer and then use it to fit and then transform our body into a bag of words. You may have heard this term before, bag of words. In natural language processing, when we use it, we're talking about the simplest implementation of a document term matrix. The process has converted each document into a vector. The matrix consists of a vector for each document in our body. Here's the vectors that we saw earlier. We can run bagofwords.toDense to take a look at these vectors. As you can see, the vectors match what we expect. The next step is to do our singular value decomposition. In Scikit-Learn, this can be done with the model truncated SVD. The word truncated refers to the fact that we're not going to get back as many vectors as we started with. Here we import truncated SVD from sklearn.decomposition. We create an SVD model and then use it to fit and then transform the bag of words into our LSA. This entire process has transformed our original data into topic-encoded data. The data now consists of 2 columns, one representing each of the 2 topics that we requested from the truncated SVD. Recall that this value of 2 was passed as an argument to the truncated SVD in the previous step. Next, we're going to use the Pandas library to look at the output of our LSA. Here we can see the 4 original documents that we started with, and then a numerical value according to each of the 2 topics. Note that all 4 documents are strong in topic 1. But there is a clear distinction for topic 2 between the second and third documents and the first and fourth. If we look at it, we can intuitively tell that this probably has to do with the fact that the first and fourth documents are about foxes, whereas the second and third are about dogs. One great thing about a latent semantic analysis is that it generates a few byproducts that can help us to understand what each topic is encoding. 2 byproducts that we're going to look at are the dictionary and the encoding matrix. Remember that the dictionary is the set of all words that show up in at least one document in the body. The encoding matrix was used to encode the documents into this topic-encoded representation. It can be examined to get a greater understanding of what each topic represents. Let's take a look at the dictionary. The dictionary is an attribute of a fit count vectorizer model. It can be accessed using the getFeatureNames method. Here we see the dictionary for our trivial example. The words brown, dog, fox, lazy, quick, red, slow, the, and yellow. The encoding matrix is made up of the components stored as an attribute of a fit truncated SVD. We can examine this matrix to gain an understanding of the topics latent to the body. Let's take a look at this encoding matrix. Here, each row represents a word in our dictionary, and each column one of our 2 topics. The numerical values can be thought of as an expression of that word in a given topic. Next, we'll interpret the encoding matrix. We might be interested in what are the top words for each topic, or what dimensions in word space explain most of the variance in the data. Note that we're going to need to look at the absolute value of the expression of each word in the topic. A word that has a strong negative representation is just as important as a word that has a strong positive representation when we go to interpret the topics. Let's take a look at topic 1. As you can see, the most important word is the word the. In later videos, we will look at removing words like the that don't have a lot of meaning. Let's take a look at topic 2. As you can see, the two most important words are fox and dog. But let's take a look at the original calculation. We can see that fox is very strongly positive, while dog is very strongly negative. What this is telling us is that topic 2 is going to be a great topic for helping us to represent whether that document is about a fox or about a dog. You might even say that topic 2 is a measure of a document's foxiness. In the next video, we'll look at a slightly more complicated data set.